All right, let's check out some example problems. So here is a problem. So we have pins A, B, and C. They have a diameter of 0.5 inches, and they're loaded in double shear. You want to compute the shear stress in each pin. Okay? So let's do it right here. Given we have F is 2,500 pounds. Diameter is 0.5 inches. We're going to find tau at pins A, B, and C. We're going to assume double shear. Let's have a sketch up here of a free body diagram. And I'm going to look at just the right side, okay? And we can look at basically by, bx. Here's point C, and this has a force FAC. This is location C, and this is our force F. Okay? So, let's get to the solution. Summation of the moments at B set to 0. Assume that way is positive. So we're on this beam here. We sum the moments at B. Then we have F times what? 50 inches plus 25 inches, which is 75 inches, right? The horizontal distance, minus FAC times 60 inches. Set that to 0. So this is 2,500 pounds times 75 inches. That'll equal to FAC times 60 inches. So FAC becomes 3,125 pounds. And I'll do it over here because it's kind of the same. If we sum the forces and the x, set it to 0, we have bx minus FAC equals 0. Then we have bx equal to the 3,125 pounds. We sum the forces in the y, set those to 0. We have by minus f equals 0, and by then becomes 2,500 pounds. Then what we need to do is, because B is at an angle, we got to find B by taking the square root of this bx squared plus by squared, because we're going to use that in the calculation. So 3,125 pounds squared plus 2,500 pounds squared, and we get B to be 4,000 pounds. Okay, now we found the reactions, the forces. We can now find tau. All right, and let's do at A and C. So tau, did I put find up here? Yep. Fs over As, and we're doing double shear. So this would be FAC over 2 times the area, pi d squared over 4. So this is 3,125 pounds. 2 times pi times 0.5 inches squared over 4. So the tau in those pins with double shear is about 7,960 psi. Now if we want to find at B, tau is again Fs over As. We're doing double shear. 4,000 pounds over 2 times pi, 0.5 inches squared over 4. And tau, it would be 101.90 psi. Okay. So this is an example of direct shear stress. Okay. Now let's look at torsion. Okay. So example 2.4. Compute the torsional shear stress due to a torque of 88 pound-inch and a circular shaft having a 0.4 inch diameter. All right. So some things you want to know is, okay, we're dealing with torque. We have a complete shaft, and in your appendix you have a shaft. Here's a circle. You got area, you got moment of inertia, you got surface area, you got some other areas, polar moment of inertia, and you're going to need to know this ZP, okay? Because you use ZP to find the maximum shear stress, okay? Torsional shear stress. And it's different for a hollow circle. You got different parameters. You got a square, okay? And then there's more examples on here, okay? Now, if it was a hollow, you have different shear stress, okay? So here is an example of a shaft with its shear stress, okay, torsional shear stress. And then down here is the hollow shear stress, okay? Just to show you exactly what's happening here. There's a torsional shear stress that's happening that, if it's too much force, would actually break. So in order to do this one, all right, let's go ahead and do the problem. So given we have torque of 88 pound-inch, we have the diameter 0.4 inches. All right, we're going to use ZP is pi d cubed over 16. We're going to find tau max, and we have a shaft, okay, so we can do a sketch. Here's the shaft, okay, and then the solution for torsion, for tau max, the shear max stress would be T over ZP. And you just got to make sure you use the right formula. Pi d cubed over 16. So tau max equals 88 pound-inch over pi 0.4 inches cubed over 16. So tau max becomes 7,000 psi. All right, now here's an example of a hollow one, okay? So compute the torsional shear stress in a hollow shaft with an outside diameter of 40 millimeters and an inside diameter of 30 millimeters when it's transmitting 28 kilowatts of power at a speed of 45 radians per second. All right. Cool. So given, we have W dot, or in this book it's called P, 28 kilowatts. We have omega, or N in this book, which is 45 radians per second. The inner diameter they call little d, 30 millimeters. And then the outside diameter they call d, which is 40 millimeters. We have a hollow shaft, so ZP is pi d to the fourth minus little d to the fourth over 16 times d. Sketch, we have a hollow shaft. Okay. All right, we're going to look for tau max. So let's get to the solution. So first we got to find torque. So torque is power over N, revolutions. So we get 28 kilowatts, going to convert that, so there's 1,000 watts in 1 kilowatt, divided by 45 radians per second. So this becomes 622 Newton meter per torque due to that power. And then now we're going to find tau max. So tau max equals T over ZP. Again, use the right formula. Pi d to the fourth over little d to the fourth over 16 times d. And let's go ahead and plug this in. 622 Newton meter over pi 0.04 meters. I converted it. 0.03 meters to the fourth over 16 times 0.04 meters. Our tau max becomes 72 megapascals. Okay. So, a couple examples of torsion and finding the maximum shear stress. Okay, which, to go back over here to this, okay, it's going to happen at the outside, at the far ends of these. Okay. All right. Let's do an example of shear and moment diagrams. I'm just going to move this over here, blow this up. So what we have here is basically some sort of bar that's, we got 800 pounds being applied at an angle off like a 90 degree. We're assuming that these points A and C, okay, they have no moment, and they're simple supports. Okay. And one of them will pick to have the X direction. That doesn't really matter right now. Okay. So what I like to do is go ahead and redraw this between those 2 points, A, C. Draw this down. This is B. And let's break this 800 up into components. So you'd have 800 times sine of 30, which gives, should be 400, because sine of 30 is 0.5. Okay, and then we have the y direction going downward, which is 800 cosine 30, which is 693. And let's put the pounds on here to be complete. All right, we have a reaction I'll call RA over here. We have a reaction RC here. And then we have dimensions, okay? So over on the right, I'm going to find those reactions. So I'm going to sum the moment at A and set it equal to 0. That way is positive. So we should have 693 pounds times 22 plus 14 inches. Okay. So it's this 22 plus that 14 because it's acting that far over. All right. Then we have minus 400 pounds times 22 inches. Okay, because it's this 400 pounds is acting 22 inches like away from point A. And then we have minus RC times 22 plus 60 inches. And that's set to 0. Okay, so that is, like, there's a reaction here, RC, and that's 60 plus 22. So when you do the math, RC becomes 197 pounds And now if we sum the forces in the y, set it equal to 0, you have RA plus RC minus 693 pounds equals 0. RA plus 197 minus 693 pounds equals 0. RA now is 496 pounds. Alright, so we found the reactions. Now we can do the shear and moment diagram. So let me draw this again right here. And what we're going to do is pretty much calculate the moment at B based on those two 400 and 693. And we'll assume this way is positive. So we get minus 400 pounds times 22 inches plus 693 pounds times 14 inches. And this moment now becomes 902 pound-inch. And that's acting at B. So we'll call it MB. Okay. This is A, this is C, this is still point B. And let me do that in orange. MB. Okay. Now, let's go ahead and draw. This would be the shear. So pound is a function of this location. So the reaction at A, so this is going to go up. And it might not be to scale. This is 496 pounds. And it's going to go over to B. Okay. And then the reaction at B here was 693. So you're going to go all the way down 693. That is definitely not to scale. Let's go to maybe right here. So this point now, this is 197 like we calculated at RC. Okay. Then it's going to go over and stop. Okay. I can fill this in. So that's how your shear would look like. And again, we just moved everything up to point B. And then if we look at the moment, go ahead and draw this from here to here. I can put dots here. So again, it doesn't have any moment at A and C because there's 0 moments. And what's going to happen is the reaction is 496. So we take 496 and we multiply it by 22 inches because it's 22 inches between here. Okay, this is 22 inches. So when we do that, it's going to go up to right here. Okay. This is a simple rectangle. You just take the area. That's your moment increase. Okay. So this value is 109.12 pound. This will put moment pound inch, right? Shear and moment diagrams. Now, it's going to go up, straight up, because you have that moment B, which is 902. Okay, so this would become 11814. That's 902 pound-inch straight up. Okay, so this distance here is 902. Then it should go right back to 0. Again, oh, that's not bad. Kind of tricky here drawing a line here. It's a rectangle. All right, so this would be pretty much like a triangle shape. And this will go pretty much back to 0 because we can check. Let me do all this. Blue. So this number should pretty much get right back to 0, and you can check. It would be 197 times 60. Okay, so 197 times 60 gives you 11820, which is pretty close, just with rounding everything with 11814. Okay. So this is an example of a shear and moment diagram that has some sort of L bracket with a force acting off on the side. Okay. basically break up the components, calculate your reactions based on the location of the force, and then in your shear and moment diagrams, we just kind of move that back to B. You have a moment at B now. You have these reactions. You can draw your shear and moment diagrams. Okay? All right. I hope this helps with homework 1.